mass spectrometry is a technique, it's an analytical technique that allows chemists to measure the mass to charge ratio of ions. And most of the time, we're specifically looking at positive ions, okay? So the most important thing that I want you guys to recognize here, in this technique, we only are detecting species that have a positive charge. If they're neutral, we don't detect them. Okay? So in some of the things I'm going to teach you, we're going to generate positive ions, but we're also going to generate neutral molecules. If it's neutral, we don't observe them. This technique specifically only works to measure mass to charge ratios of cations. Okay? The reason to teach mass spectrometry is that it's one of the more valuable tools that helps us determine molecular weights. Okay? So that's the easy part of all this. But the interesting part of this is that we often get information about structure. If we analyze specifically how this molecule, what happens to this process of basically relieving its energy through a process called fragmentation. Okay, so one of the things I'll be talking about momentarily is in order to make ions, we're going to bombard this molecule with electrons. And this electron beam is going to have a lot of energy, and it's going to permit us to start exciting up this molecule. And this molecule, the only way it can relax is by basically breaking bonds. And it breaks bonds in really interesting fashions that are very predictable. And the way the molecule fragments, breaks into these smaller pieces, often gives us a little bit of information about the structure. Okay? Now, I also want to point out that today, and for the past several years, this is the most effective way to sequence proteins. Okay? It's fast, it's easier than doing it the old-fashioned way. One final thing I want to just point out to you, notice that this technique is not called mass spectroscopy. It's not using electromagnetic radiation. Like we learned, you may have learned about infrared spectroscopy, you might have learned about NMR spectroscopy. This is called spectrometry because it's a different type of technique. Okay, it's not using radiation from electromagnetic spectrum. This is an example of a molecule that has undergone, that is basically looking at its mass spectrum. Okay, so what I have here is one pentanone. Okay, one pentanone has a molecular weight of 88. Okay, one of the things I want you to first recognize is that I have this horizontal axis. This has masses. This is about where 88 shows up. Okay, notice it's really small. Actually, I don't see an 88, I see a -1 peak. Okay, so actually the mass that I'm recording is not 88, but 87. So one of the questions is why? In addition, don't you see that up here, there's an intensity. So the y-axis is measuring intensity, whereas the x-axis is measuring basically the mass. Notice that the smallest masses, the largest mass is the mass of basically the molecular weight species, and then every other one is the other parts of this graph are smaller components, smaller fragments of that molecule. Okay? Notice some are very large and others are very small. Now, what's very predictable is often these larger peaks. Okay? So you can see that there's a mass that corresponds to losing water. So if I took 88 and basically take 88 and subtract what's water, 18, I get a mass at 70. So somehow we're going to have to learn how this molecule loses water under this technique. Here's another peak that's basically loss of water and a methyl. Can we make that prediction? Here's another example where I lose water and a molecule of ethylene. And then here's another molecule that this is a fragment. Can we make that prediction? Okay, so we're going to kind of look at that. We're going to look at basically how these molecules fragment. But one of the more important things I want you guys to also see in this is that often the peak that we want to measure the molecular weight is often very small, and sometimes it's not even present. Okay, so one of the other things I'll be talking about is another technique later on that specifically permits us to look at molecular weights, because oftentimes with this type of process, we don't often see the molecular weight. Okay. Also, once again, just to reiterate myself from the preceding slide, notice that the peaks I've assigned here all have a positive. Okay, so this corresponds to a positive. Notice I have a positive here, a positive here, a positive here, and a positive here. Now, I won't get into this, but I'll right now, but again, I just want you guys to also recognize there's two types of positives that we will talk about here in this chapter, and that is the traditional positive charges that you've seen. So if you saw a carbocation in the past, if you've seen oxygen with positive charge, that's this guy here. We have a new positive. And notice these positives are what's called a radical cation. So we either are going to generate cations or radical cations through this process. Okay? So this is a molecule that has lost an electron, and by default, it makes it positive. Okay? And again, we'll look at this stuff in a moment. So one of the things I want to point out to you guys is that in some of the mechanisms I'm going to propose on how these molecules break up, I will be using arrows that are double arrowhead, as well as single arrowhead arrows. Remind yourselves, when I use a double arrowhead arrow, that implies I'm breaking and I'm moving 2 electrons in that bond. On the other hand, if I use a single arrow, I'm only moving 1 electron. And I have to do that because we have radicals. So it's also an opportunity for me to revisit radicals a little bit with you guys. Also revisit carbocations in this chapter. Okay, so like I said, the stuff that Dr. Schwann has gave me to teach you guys, a lot of this is going to be review chemistry. Okay, so again, I'm going to try to make connections. I'm going to try to help you out. It's not that bad of a chapter because you've seen a lot of the chemistry already. So again, before we go off, the x-axis again it represents the masses of positive ions. Okay, and notice right off the bat, I don't have anything larger than this molecule here. Okay, and that's very interesting because one of the things you may have learned in radicals is that radicals often do dimerize, right? If you form a radical, it wants to react with itself. So one of the things you probably learned is if you take methane and treat it with chlorine, you also get ethyl chloride because the 2 methyl radicals can react with one another. Inherent in this technique, and when I describe this instrument to you, what we're going to do in this technique is actually minimize the ability of 2 molecules to come together. So that all we're going to be doing is how this molecule can dissipate its energy within by breaking up into smaller fragments. So we're essentially setting it up so that the molecule can't react with the second molecule. The y-axis, again, represents the relative abundance of each ion. And again, it's relative. It's relative in that we assign the largest peak here. This peak here is, by definition, whatever shows up as the largest peak, we define it as 100%, and this is called the base peak. So if you hear me say the base peak, that's a peak that's the largest, and by default, we define it as 100%, so everything is relative to that 100%. Okay? Now, what's really interesting is the characteristic of these ions obtained in the abundance is really characteristic of the structure of a particular molecule. Okay? So if I had 1 pentanol, 2 pentanol, 3 pentanol would look different because they're constitution isomers. So in essence, mass spec is also an effective way, just like IR was used as a fingerprint. Many drug labs also use mass spec to basically analyze what's in what they're analyzing. Okay, because again, every mass spec is very distinguishable of every compound. So let's talk about the instrument. The instrument really tries to do three things. First, it converts neutral atoms or molecules into a beam of positive ions. Okay? And so I say negative ions too. There's some faculty years ago that used to do negative ions, but for the most part, from this point on, we're specifically going to say what we're going to do in this technique in this chapter is we're going to convert neutral atoms and molecules into a beam of positive ions. Okay? And the next part is the instrument needs to separate the ions on the basis of their mass to charge ratio. So once I take these molecules, how can I see and measure the different fragments? And then the last thing that we have to do is measure the relative abundance of each ion. Okay? So here is a schematic of an instrument. And specifically here, there's different types of mass spectrometers, but this is the one that I'm going to be asking you to use what I'm going to teach you on. The most general mass spectrometer, the one that's been around the longest, is called electron impact mass spectrometer, EIMS. And specifically here, we're going to add electrons to the molecule and really, really get it excited. And so in here, this is where the sample comes. This is where the molecule enters. At some point, one of the things I have to do is basically what we're going to be doing here is as soon as I'm going to take this molecule and I'm going to vaporize it, get into the gas phase. Why do I want to put it in the gas phase? Well, one of the things that you've learned in general chemistry is gases don't collide, right? Particularly if they're ideal, okay? So we basically want a system where two molecules that form radicals can't react with each other because they would dimerize and I can't determine the molecular weight. So in order to do this, we're going to first convert the molecule to the gas phase, and specifically we're going to use very low pressure to minimize the concentration of molecules reacting with each other. So what I have here is, again, the molecule basically goes into a gas beam, and once it gets into the gas phase, it sees this filament here, and this filament will provide a beam of electrons. Okay, and once it has a beam of electrons, it forms ions. The ions get filtered through this, and eventually we're going to use a magnetic field here to basically get molecules, different fragments, to come in and focus at different times. Okay, so we're going to do that by varying the magnetic field here. So by varying the magnetic field here, we're going to be able to separate the various mass to charges that come out. Okay, and then we have a collector beam that collects it, and then will tell me the relative abundance. Okay, so I'm going to finish off these two slides, and I promise we'll take a break. So what happens then is, in the first part, the molecule is bombarded with a beam of high energy electrons. And what happens is, here is ammonia, okay? And recognize ammonia has 3 sigma bonds to an NH, and it also has lone pair of electrons, okay? By default, lone pair of electrons, since they're not bonding, are more available, right? In that they're more accessible, they're not held as tightly. So as a consequence of this, the electron that the beam of light hits will take off an electron to make this radical cation. Okay? So notice this is a radical. Instead of having 8 electrons around nitrogen, I have 7. If you think about how one calculates formal charge, I have basically nitrogen, it has 5 electrons, right, by the periodic table, 5 valence electrons. And I have 3 bonds here, where each one of those electrons is being shared. So I have 1, 2, 3, and the radical 4. 5 minus 4 gives this radical a positive charge. Okay, so this is basically a radical cation. Okay. Now, in the next step, in this ionization chamber, just to give you an emphasis, not only have we vaporized this molecule, but in the ionization chamber, we're in a vacuum where the pressure is really, really low. Okay, so 10 to the minus 6, 10 to the minus 5 torr, or millimeters of mercury. Okay, so we're in a very, very high vacuum, and the reason for this is that it basically prevents bimolecular processes from occurring. Because remember, two radicals will want to collide to make a sigma bond. But if we do this under vacuum and in the gas phase, we're really preventing bimolecular process from occurring, but instead we're looking at unimolecular process, and in this case, fragmentation. The electron beam is generated from a filament, and just to give you an idea what we're talking about here, we're supplying 70 electron volts. 70 electron volts corresponds to about 6,750 kilojoules per mole, or 1,600 kcals per mole. Okay. Remind yourselves that most organic molecules ionize in between 8 to 15 electron volts. So we're beating this molecule up, right? It only needs 18 to 15 electron volts. We're supplying a lot more. So this molecule is going crazy. It's really exciting. And so the real question is how does that molecule, once it's so excited, how does it dissipate energy? One of the most effective ways of dissipating energy is by breaking bonds, okay? But before I go into that, let me just say, now that we have this, after these ionization chambers, cations enter that analyzer tube, okay? Recognize I lower the pressure even further. Why? Because I'm using a pressure gradient to basically go from here over here. So the way I'm getting these beams, these ions to travel is by changing and reducing the pressure. Okay? So of course, in order to have a pressure gradient, I have to have a lower pressure in the ionization chamber after ionization. Okay? The magnetic field is applied, increased, which brings ions into focus and is collected. Normally we scan between 12 and 500 AMUs. And this is the equation that one uses to vary the magnetic field. So what I'm talking about is, in order to get different ions to travel, we're going to vary this magnetic field. Some of them are going to crash in here, and others are going to go right through, and others are going to crash. We're going to vary this magnetic field at different times so that we can start to see the different mass to cation ratios. Mass to charge ratios, I should say. Okay. So again, the fragments are sorted according to the mass to charge ratio. Most of the fragments detected have only a +1 charge. Okay. Can we see +2? Yes. But most of the time, we're only looking at +1 charges. So it really makes this process a lot easier. And this is what we're kind of doing here. So the mass to charge ratio is equal to magnetic field times the radius divided by the voltage. Okay, so by varying the voltage or magnetic field, I can get different curvatures and get the ions to focus at different rates. Okay, so that's in essence what we're doing here. That's how the process works. So the next part after the break is how can we use it? Okay, so go ahead and take a 5-minute break, and then we'll resume.